In this lecture we're going to look at sequences, and a sequence is just a list of numbers where the order in which you write them matters. It might be an infinite sequence or it could be just a finite sequence. And when referring to a sequence abstractly, the nth term of the sequence is the nth number on the list. So the first term of the sequence is the first number on the list, the second term of the sequence, the second number on the list, etc. And we often use subscripts to denote the nth term, or perhaps functional notation. So in the abstract sequence I've written below, a subscript 1 denotes the first term, a subscript 2 the second term, a subscript 3 the third term, and so on. And these a's represent numbers. Here's an actual example of a sequence, the sequence 1, 2, 3, 4, 5, 6, and you see the terms are separated by commas, and once you get the idea of what's going on, these dots represent the mathematical equivalent of etc., etc., etc. So we have a subscript 1 is 1, the first term of the sequence is 1, the second term is 2, the third term is 3, and we can see by the pattern the nth term of the sequence is going to be n. So if this pattern continues, the 100th term of the sequence, a subscript 100, should be 100. Some sequences have patterns and some do not. If I took a 20-sided die and rolled that die repeatedly until the cows came home, then I would generate a sequence of numbers which had no pattern. I couldn't predict what the next number in the sequence was. I wouldn't have a formula for it. I do know it's going to be a number between 1 and 20, but I don't know which one it's going to be. On the other hand, the sequence we looked at above does have a pattern, and I can actually write down a formula for the nth term. A subscript n is n, and this alternating sequence where the terms alternate between 1 and -1 has a pattern. I can always tell what the next term is going to be. It's either going to be 1 or -1, and if the current term is 1, it's going to be -1, and vice versa. We can find a formula sometimes for the nth term of the sequence. We can figure out what the pattern is and write down a formula for the nth term. And we've already done this for the sequence 1, 2, 3, 4, 5, 6. We know that the nth term is going to be n. And let's look at a few sequences and try to write down formulas for the nth term. Now this is a very important sequence, this alternating sequence that alternates between 1 and -1. Notice that the nth term here can be described by -1 to the n plus 1. -1 to the n or -1 to the n plus 1 will alternate between 1 and -1 as n runs from 1 to infinity. And in this case we need -1 to the n plus 1 because when n is 1 we want a subscript n to be 1, and when n is 2 we want this to be -1. Here's another sequence, and you can try to figure out a formula for the nth term. The first term, when n is 1, it's -1/2. When n is 2, it's 1/3. When n is 3, it's -1/4, etc., etc. So this one has the alternating pattern, but it also has a fraction which is associated to the n. That fraction, you've probably figured out, can be written as 1/n plus 1, and the alternating pattern we can catch using -1 to the n. So a formula for the nth term here would be -1 to the n over n plus 1. And you can check that out, that fits A1, A2, and now you can predict that the 100th term will be -1 to the 100th, which is 1 over 101. Factorials are commonly used in sequences and their descriptions, And let's just review what a factorial is. 0 factorial by definition is 1. 1 factorial is 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. And for any number n, n factorial is n times n minus 1, etc., etc. It's n multiplied by every positive integer less than n and greater than 0. So, for example, 9 factorial is 9 by 8, by 7, by 6, by 5, by 4, by 3, by 2, by 1. So let's look for a formula for the nth term of the following sequence. And you might guess, because we've just looked at factorials, that it has something to do with factorials. And you need to be used to calculating factorials here to realize that they're involved. So we have 2 factorial is 2, 3 factorial is 6, 4 factorial is 24, 5 factorial is 120, and a1 here is 2 over 1, a2 is 4 over 2. So you can see the denominator is going to be n factorial. And now the numerator, you might be able to recognize what's going on here. These are powers of 2. 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8. So a formula for the nth term here would be 2 to the n over n factorial. Now, when we're representing a sequence, we can do that in many ways. Here are 3 very common ways. We can give the first few terms, which show the pattern, and then give a general formula for the nth term, and enclose our list in curly brackets. We can just forget the first few terms and just give the formula for the nth term and enclose that in curly brackets and say that our n runs from 1 to infinity. So this means that we're looking at a list where the list starts with n equals 1 and runs all the way up through the integers to infinity, and the formula for the nth term is n over n plus 1. And lastly, we can just give the general formula for the nth term, an equals n over n plus 1, and then it's assumed that the n start at 1 and run to infinity. So the second sequence, b, we can again describe that in any one of these 3 ways. The first few terms, minus 3 over 3, 5 over 9, minus 7 over 27, and the general formula for this alternating sequence is minus 1 to the n times 2n plus 1 over 3 to the n. And we could also write it in the more compact forms by either just giving the formula for the nth term an, or putting the formula for the nth term in curly brackets and saying the n runs from 1 to infinity. And we have a third sequence, sequence c, e over 1, e squared over 2, e cubed over 6, etc., etc. The general formula for the nth term is e to the n over n factorial. So again, we can represent that in any one of the 3 ways